Okay, so we're talking about nonparametric Bayes and exchangeability so far. We've mostly talked about nonparametric Bayes. And again, we're trying to learn more from data as we get more of it. And so let's just recap where we are at this point. We have introduced the problem of clustering. We've been developing nonparametric Bayes for clustering. And to that end, we have defined the GEM distribution, which you had homework for over lunch. And we'll talk about that in a moment. We are about to define the Dirichlet process. We actually didn't quite get there. We got to Dirichlet process stick breaking, and we're about to really get there. The big questions that should be in the back of your mind throughout this first part, and we're going to revisit them very briefly after we define the Dirichlet process, are why nonparametric Bayes? Why are we doing this, especially from a practical perspective? What does it mean to have an infinite number of parameters? What does it mean to have a growing number of parameters, and what does it mean to do that at the same time? Why is nonparametric Bayes challenging, and why might it be practical? In the second part of the talk, which we're going to get to pretty shortly, we're going to talk more generally about how this nonparametric Bayes stuff we've been talking about fits into a general discussion of exchangeability. In particular, we're going to talk about the Kingman paintbox, and then we're going to talk about other types of D-Finetti mixing measures that are useful, in particular in the context of networks and graphs. And so we'll get a sort of a general sense of how we can use these D-Finetti mixing measures and what might be the challenges that arise from that. And the question we're going to want to ask there is, how does thinking about exchangeability help us use nonparametric Bayes methods and, in fact, Bayesian methods in general in practice? Okay, so let's recall that what in particular we had been focusing on again was this clustering problem. And so we had talked about a few different types of Gaussian mixture models. We talked about a two-component Gaussian mixture model where we generate the proportions rho 1 and rho 2 from a beta distribution, or to be more exact, we generate rho 1 from a beta distribution, and rho 2 is 1 minus rho 1. Then we extended this to a more general finite number of mixture components where we generated the component proportions from a Dirichlet distribution now, so rho 1 up to rho k. And then basically where we had ended was we talked about extending this to the case where we just don't sort of run out of components, these unfilled or filled clusters. We want to be able to sort of go to infinity. We want to be able to always have an unbounded number of clusters that we can call on in our work. And so we introduced this GEM distribution, this Griffiths-Engen-McCloskey distribution. And in particular, the defining feature of this GEM distribution was that we just kept breaking off beta distributed proportions of our stick of mass 1. So we'd bake off a beta 1 alpha, then a beta 1 alpha of what's left, and then a beta 1 alpha of what's left, et cetera. And so this is the point at which we had been looking at this demo, and so let's just revisit it now. And so in particular, we had our GEM draw. Oh, is it already up there? There it is. Okay, we had our GEM draw, and this is with a parameter 10. So the alpha parameter is 10. And so one of the things I asked you to think about over the break is remembering that these breaks are size beta 1 alpha. Now let's suppose I take this parameter and I make it 1 instead of 10. What's going to change about this GEM distribution? Okay, so the proposal is that we'll see perhaps more concentrated clusters. Maybe we could say just a little bit more about like how we think the visual will change. Yeah, okay, so you think that maybe these will be big? Okay, so the observation, remember with beta 1 alpha, we talked about this before. So whichever one of these is bigger, the corresponding row tends to be bigger, right? So there's sort of this rho 1 and rho 2, if we were drawing them from beta 1 alpha. And so if 1 tended to be bigger, then rho 1 would be bigger. And if alpha tended to be bigger, rho 2 would be bigger. So if we compare 110 to 11, it looks like we're sort of decreasing alpha. But the part we're keeping is the first part. So let's see if that intuition holds. So let's draw. Now I'm putting in alpha equals 1. I'm putting it over here. And so the thing to keep in mind is that, of course, the number of components won't change. It's always countable infinity. But visually, the relative sizes of things will change. And so in particular, based on this intuition we just discussed, in which a number of people in the audience said, we're going to be seeing bigger, on average, I mean, it's all random. We're just making beta draws like we did before, bigger on average groups in the beginning. And of course, eventually it has to get smaller and add up to 1. And so we can make a few draws from this. It's worth noting that, of course, there is no strict ordering to these. The first one does not have to be the biggest one. And we see that in some of these draws because it's just a beta 1 alpha draw. But they tend to be larger than we saw before. And so hopefully it's pretty straightforward to think about what's going to happen now if we change the parameter in the other direction. What if we went from 10, an alpha of 10, to an alpha of 1. Now we're going to go to an alpha of 100. So think in your mind about what you expect to happen. And now compare it to what we're seeing on the screen. We're seeing much smaller groups to begin with. Yeah?
How long does it take for me to cover, let's say, 1 minus epsilon fraction of this thing?
Yeah.
Is there sort of a qualitative phase transition where alpha greater than 1 alpha doesn't?
Yeah, so I mean, certainly you could just make an argument based on the expected value of all these betas and say like, oh yeah, there's going to be some exponential thing where I cover this. But I think an interesting point that's related to the point of like how many of these do I have to generate to get to some 1 minus epsilon mass is that I think one of the things that we're probably all thinking in our minds is, gosh, how are we going to actually do this in practice? Are we going to have to make some kind of epsilon approximation? And something that we're going to see very shortly is that perhaps we might not even have to make any kind of approximation, which will be cool. OK, so at this point, we have this GEM distribution. We have the ability to simulate from it. We know about it. And so now what I'm going to do is I'm going to keep building up the mixture model. Yeah?
So one of the intuition also, if I have beta 1, 1, for example, is that it tends to concentrate around 1/2. So if I want to, what parameter do you recommend I use if I want to have, I want to move along the axis of having small blocks, but or big blocks, but also want them to have different sizes, a variety of sizes, or sort of homogeneous sizes.
OK, yeah. So there's an interesting question in here. I'm gonna interpret your question as basically we want different behaviors in our ability to grow clusters. And actually, one interesting kind of point that came up in your question is, what if I want homogeneous sizes in my clusters? Something that I actually cannot get from the GEM is homogeneous sizes in my clusters without bound. So if you think about it for a moment, I just can't have equally sized probabilities without bound. And so something that we're going to, let's keep this question in mind when we talk about the exchangeability part, because basically it's going to come up there. Now, something that definitely comes up here, and this was another sort of thought question for over the break, is you do get different behaviors from different choices of alpha. And there are behaviors that you simply cannot get from within the GEM. And so one of the things we're going to talk about later are what are some of the behaviors you can't get. But I'll tell you right here now some things that we're not going to talk about going forward. So one is the number of clusters grows basically like alpha log n. So alpha, a larger alpha, we just saw, is going to make it look like there are a ton of clusters visually. And so we're going to fill those up much more quickly. And so that's roughly the intuition about why we get a larger alpha giving us more clusters. But something else that's really notable about here is that you get this log n growth, where n is the number of data points so far. A lot of things in real life are power laws. They're not log n. And so actually you can do something different than the Dirichlet process, what's known as a Pittman-Yor process, to get power law growth. But there are basically certain behaviors you can get with a beta, with a Dirichlet, with a GEM. And in some sense, what we're talking about today is, OK, well, each time we get a new model, what are the limitations and the things that do work about that model? OK, so let's fill in this discussion. So we had sort of these slides earlier that were like, here's what a 2-component mixture model looks like. Here's what a k-component mixture model looks like. Now let's talk about what a GEM mixture model looks like. And eventually, in the course of this slide, you can see we're going to define what a Dirichlet process is. OK, so just like before, we had our Dirichlet, and we had 3 components, and they had these different probabilities, row 1, row 2, row 3. Now we have row 1, row 2, row 3, and it just doesn't stop, and that's what the ellipsis is suggesting. Just like before, we would draw the means for all of our clusters. Now we'll draw the means. Something you might immediately be thinking is, we're not going to draw an infinity of means. That's not really practical, and we'll get back to that point. But for the moment, let's pretend we do. We draw means for all of our clusters. Now, one way that we could express these 2 steps is as I've written them. We have some distribution over the integers, and we have some set of means, and they're just going to be linked by the indices. Like this is the probability of the first cluster, and this is the mean of the first cluster. This is probably the second cluster. This is the mean of the second cluster. But something that's a little bit annoying about that is that there's actually no ordering on clusters, and so it's sort of an awkward way to express that. And so I'm going to show you the exact same idea as in these first two lines, but an alternative expression for it that gets rid of that ordering. And so in particular, what we're going to do is instead of having row 1 associated with its index and then mu1 associated with some mean, we're just going to put row 1 on top of mu1, and we're going to put row 2 on top of mu2. We're going to put that mass directly on the value. I'm still going to index it in my notation just so we can go over everything, but you'll notice that this measure now doesn't have to use indices to sort of relate it to something else. And in particular, the way that we would write that is we would write it as this measure g. So this is just a way of saying that we're going to have some mass located at mu k, and then the size of that mass is going to be rho k at mu k. So basically, we're choosing the cluster with center mu k with probability rho k. This is a probability measure. Now, to say that the rows are GEM distributed and the mu's are normally distributed, a completely equivalent way of seeing that, and the way that you will often see it in papers if you're reading papers in this area, is to say that this measure g is Dirichlet process distributed. So we're finally defining a Dirichlet process here. The Dirichlet process gives us a distribution over these measures, and it has two parameters, alpha, which is just the GEM parameter that we're now familiar with, and the second parameter is a distribution, and that distribution is basically the prior on the cluster-specific parameters. In this case, it happens to be cluster means. You don't actually have to stick to Gaussian mixture models in this framework. You could do something else. Okay, so again, we're going to keep building up what does this Gaussian mixture model look like with a GEM. So the next thing we would do is we would draw the assignments of data points to clusters. Again, from a categorical, just like we did for the beta and the Dirichlet. So this is just saying now rho is this countably infinite vector, rho 1, rho 2, rho 3, et cetera. So we're saying we're going to draw 1 with probability rho 1, 2 with probability rho 2, 3 with probability rho 3, et cetera. So it's going to be for the nth data point, what cluster does it belong to? And then let's just say what is the parameter that we're going to associate with that data point. If it belongs to the first cluster, then it's going to somehow appear around this first cluster mean. So that's all that mu n star means. It means what's the parameter, the cluster sort of specific parameter associated with this data point, with the nth data point? It's mu sub zn. Okay, so just like up above, I said, hey, these two lines are equivalent to this line. This is just sort of a notationally different way to write the two lines above. I'm going to do the same thing over here. I'm going to say these two lines are equivalent to the next bullet point I'm going to put down. And that bullet point is the following. We draw the cluster parameter for the nth data point from the distribution G. So G is a distribution. It's just a distribution over the cluster-specific parameters. Here it's the cluster means. And now what we'll do is for each data point, we'll say, well, what parameter does it come from? What cluster does it come from? Finally, now that we know the parameter that this data point is drawn around, we draw its actual value, xn. So that's going to be like the points we actually see with some likelihood around that cluster-specific parameter. Now, again, I want to emphasize, this doesn't have to be for Gaussian mixture models. You could do this with topics. You could do this with all kinds of different data, in which case you would change the prior on the cluster-specific parameters, and you would change the likelihood. But you'll always have, in this type of model, one of these distributions over cluster-specific parameters that's given by a GEM, and in that case, you'll have a Dirichlet process. Okay, so if you have any questions about this notation or this setup, feel free to ask at any time. I'm about to go into a demo of what this looks like, but you can still ask questions about this notation and everything during the demo or after the demo or anything like that. Yeah?
So if you change the normal to a Poisson on the line, is that what is called the Poisson-Dirichlet process, or is it something else?
So I can't answer that specific question because a lot of people come up with a lot of names for stuff. But I think, so the thing that I would usually think of as being something that you might call a Poisson-Dirichlet process is actually there's a version of the GEM where you order the sizes of the components, and that is sometimes referred to as something like that. So that might be something that you would see as just an ordered version of the GEM. But certainly something that you could do is you could say, hey, I actually have, something that would be actually very common is you might have count data. So this would be Poisson, and then this would be a gamma because that's like the conjugate prior for the rate of the count data. And certainly you could do all kinds of stuff like that. These don't have to be conjugate. It's just that you can do all these like very nice exact samplers when things are conjugate. Yeah.
I would like to suggest a definition for the Poisson-Dirichlet process. I would take K to be a Poisson distribution and do a Dirichlet on K points.
So, yeah, so something that you can absolutely do is put a prior on the number of components and then put a Dirichlet on that. And something that's worth keeping in mind is that that's going to have different behaviors than a Dirichlet process. And I think it's something that you absolutely might want to do. You might be interested in learning something like a number of components, although there are still trickinesses with that in practice, basically due to misspecification. But that's certainly a somewhat appropriate way to do that. And it would have very different properties than using the GEM, which again will be unbounded. Whereas if you drew from that, you would eventually again hit some optimal or some total number of clusters. You just wouldn't know what it was in advance because it would be random. Cool. Okay, so let's see what this looks like. And in particular, one of the main questions we want to keep in mind is how could we actually draw from this in practice without ever having to draw an infinite number of things? Because that would be a problem. Okay, so there's a few things going on here, and what I want you to do first is just look at the top. So don't worry about this big bottom square, just look at the top up here. And so the first thing I'm going to do up at the top is I'm going to draw from a GEM2. So the alpha parameter is 2. I'm drawing from my GEM2, and so I'm going to draw row 1, row 2, row 3, and as we have observed, I actually cannot draw the entire vector of row because it is infinite. And so my question for you is, can you think of any way that I could draw from this generative model that we've described, this prior and this likelihood, this GEM mixture model, exactly? If I have access to common distributions like Dirichlets and Gaussians, and I can draw from them exactly, is there any way that I could draw from this model exactly without having to draw an infinite number of things?
Sample till you need because
Exactly, exactly. Okay, so the observation is I can sample until I need to stop. Okay, so let me explain this idea in a little bit more detail. So the first observation that I'm going to make is, suppose for the moment that I actually have an amazing computer of the future that can draw an infinite number of things. And so I did draw, in fact, an infinite number of rows, and I just haven't plotted them. Separately, I know that the way that I can draw from my rows is I can draw that uniform random variable independently, right? And so then wherever it falls, I know that I draw 1 with probability row 1, 2 with probability row 2, et cetera. And so my observation is, hey, I just decided, even though I knew all the rows and I totally generated them and I just didn't show them to you, I just decided to only plot the rows until they covered the uniform random variable, right? Because remember, they come from this side. I do a row 1, I plot from 0 to row 1, I ask, did it cover the uniform random variable? It did in this case, and so you don't need to know the other values of the rows. Same thing on the next draw. I draw the next uniform random variable to decide where the second data point goes. And so in this case, what I did was I said, OK, well, I already had 0 to row 1. Now I generated row 2 and plotted that. And I said, oh, does it cover my uniform random variable? It does not. Then I plotted row 3. Does it cover my uniform random variable? It does not. I plotted row 4. And it does cover my uniform random variable. So I decided not to plot anything more. Now the observation is, in fact, this uniform random variable is completely independent from the rows. And so I could have done this in the opposite direction. I could have first drawn the uniform random variable, and then drawn row 1 and see if it covered it. And then drawn row 2 and see if it covered it. And then drawn row 3. And then, because I know every one of these uniform random variables is strictly between 0 and 1, with probability 1, I will cover it in a finite amount of time. Now, I'm not saying that this is the most efficient way that you could do this. There might be other ways to do it. What I am saying is that this definitely is a way to do it in finite time. And that was the question we had. Is this even possible? OK, so now let's talk about what's happening down here. So here, I say the number of data points I've drawn so far in my generative model. This is indicating the number of rows I've had to draw in row 1, row 2, row 3, row 4 to cover my uniform random variable. And I'm going to plot a mean for each of those clusters. Technically speaking, some of these are components. They don't have data points in them yet. So each of those components. And then the number of clusters is the definition we had before. It's how many components have data points in them. In this case, it's 2. Now, finally, what's happening here is I'm plotting the data point, the xn that I actually generated given that assignment of a data point to a cluster. So one of these data points belongs to one cluster, and I give everything in that cluster a particular color. In this case, it's red. One of these data points belongs to another cluster. I give everything in that cluster a particular color. In this case, it's green. And I'm going to keep doing this. So here, I'm going to draw another data point. It happens to belong to the same cluster as the first data point. And so we see 2 data points now with the same color down here. I'm going to draw another data point. This one happens to belong to a row we've already generated, but technically a new cluster. Now, you'll see that to cover this uniform random variable, I had to generate a whole bunch of these rows, and that's why we suddenly got a ton of these means down here. OK, now I'm going to go forward 10 data points. Now I'm going to go forward 100 data points. And now I'm going to go forward 1,000 data points. OK, so something that's interesting at this point to notice is that we have 1,000 data points. We actually don't have too many clusters. We have 15 clusters. And this kind of agrees with a point that I mentioned in an offhand comment earlier, that in fact, the number of clusters in this particular model, and this is something you can actually prove pretty easily, grows logarithmically in the number of data points. That may or may not be appropriate for a particular application problem, but it's certainly worth knowing about this model. Yeah. Oh. Yes. So this is, if you believe that my random number generators and my draws from Dirichlet's and Gaussians and all of that are exact, then this is an exact sample. So I never had to truncate anything. I never had to approximate anything. I never had to do any of that to make this work. It's exact in that sense. Now, something, because we only have an hour and a half together today, I'm not going to have time to go into, is that this is basically how inference works in these models. That if you have conditional conjugacy, like your prior for a cluster is conjugate to your likelihood for a cluster, like the Gaussian means and the Gaussian data around a cluster, then you can do inference exactly. And the way that it works is basically a similar idea to this, that you have this infinite latent parameter. You could never instantiate that infinite latent parameter, but because there's only finitely many realized parameters, you can get away with only instantiating stuff for that, basically. And then the prior sort of operates outside of that. Now again, I'm not going to go into a ton of detail about this, but if you're interested, check out things like the Chinese restaurant process and slice sampling. Those are examples of sort of exacts, not having to make additional approximations beyond the sampler. Yeah?
So actually it's related to the answer that you just gave, which is it enough to actually be able to sample? Do we never need any, I don't know, gradient information or anything?
I guess it depends what you mean by is it enough. So if you want to get Bayesian posterior quantities that are pretty popular quantities, like a distribution over the number of clusters that we see for a particular number of data points, or posterior over certain cluster-specific parameters, then it's enough to sample as much as it's enough to sample for a regular finite Gaussian mixture model.
And the other slightly more technical question is, do you need to, like, is it important that you don't have to fix any in advance when you're actually doing the sampling procedure? Because you could probably imagine that you know how to sample from any conditions from their maximum, which would actually allow you to actually fix everything ahead of time after sampling the maximum.
OK, so I'm gonna answer a question, and then you tell me if I have answered your question. So I think a really interesting question that arises here is that there's some way in which we've couched this discussion of this in terms of streaming data, that in fact it should be that your number of data points is growing, because that's sort of what justifies wanting to have this ability to always be growing the number of clusters. And I think that that is a not well answered question in this field, is how to actually do good sampling in a streaming sense for these problems. Like, people have certainly addressed it, like there are empirical ways, but I wouldn't say that there's a lot of theory associated with how good, after you've made a bunch of heuristics, or after you've introduced a bunch of heuristics, how good that is as an approximation of your posterior at the end. Those are not samplers without additional approximations. Does,
You would want to sample as you stream the data, like every time you see a new data, you need to update the posterior?
it seems to me that that would be a desirable thing, to be able to get to understand how your posterior changes as you get more data, and in particular because the whole point was, hey, as we grow data, we want to be able to grow the number of clusters. And I think that if we care about being close to the exact posterior, that is not a well-answered question in the field right now. depending on how you define that. But if we care about being theoretically close to the exact posterior. Yeah. Yeah. So it's more like there's this classic thing in Bayesian posterior inference that as you get more data, you expect to know more about the posterior. And so like even just if we look at a simple parametric model, you sort of expect, oh, here's my posterior after a few data points, and then here's my posterior after more data points, and so on. Here it's a little bit more complex because you're also learning about totally new clusters that you've never seen before. But just the fact that this is true means that like the actual problem that you're solving changes as you get more data in terms of posterior inference. Cool. Okay, so at this point, we've defined a Dirichlet process. Let's just recap where we are. We've talked about clustering, we've defined a Dirichlet process, and we've started to answer these questions. Why nonparametric Bayes? We would like to learn more from data as we get more of it. We'd like to have these flexible models where the number of clusters can actually change as we get more data. Why? What does it mean to have an infinite parameter and a growing number of parameters at the same time? The infinity is the number of components. The growing part is the number of clusters. And more generally, because clustering is just a particular type of nonparametric Bayes, the infinity is the latent part. We never have to actually instantiate the infinity. The growing part is the realized part. And if you're familiar with Gaussian processes, you can also think of them in terms of this sort of scenario. You can say, hey, this is a finite dimensional Gaussian. This is an infinite dimensional Gaussian. Okay, and why is nonparametric Bayes challenging but practical? It's challenging because we have an infinite dimensional parameter. We can't store that in memory. You can't update that in finite time. That's hard to work with, even just in terms of making models. But only finitely many of our parameters are actually realized. And so that's what makes this practical to use in practice. And a lot of the samplers have the same, or in general, posterior approximation methods have the same intuition that our generative model did, that somehow you can integrate out the infinity. You can also do things like truncate. It's a different choice. But you can do this exactly with integrating out. Yeah?
With this integrating out, we couldn't get a likelihood of that set of data points that you generated in the demo, right?
No, I mean, you can get a likelihood. I guess it's tough because it depends what you mean by a likelihood. So you can certainly get a probability of the data, and it will depend on maybe like a layer down of hyperparameters. But with the Chinese restaurant process, for instance, you're going to integrate out the means. Or sorry, the proportions, the cluster proportions. So if you cared about those cluster proportions, you would not be able to work with them directly. But if you did care about them, you could actually still work with a slice sampler, which maybe integrating out isn't the best way to describe a slice sampler, but there are ways to work with them directly and still get sort of an exact sampler.
Is there a difference between getting an exact sampler and being able to say this is the probability of this, the marginal probability of seeing this data point?
No, you can still get that from a sampler. I guess all I want to say is that you don't have to make additional approximations beyond the MCMC sampler. And at least with some of them, you can actually access the rows if you care about that. Yeah. Great. Okay, so now let's move on to thinking more generally about clustering. And in particular, in some sense, the way that we got to this point was we said, here are some difficulties with a simple finite mixture model. Here are some things that we'd like that doesn't contain, that class doesn't allow us to do. And so now, we introduce this new class of models that actually allows us to do some of those things we want to do. And so now let's think about, well, in some sense, what are the limitations of the Dirichlet process that we just suggested? Or I should say, we're not going to talk about all the limitations. We're going to talk about some of the limitations. And a way that we can see that is via exchangeability. So let's just recall where we are at this point. We've talked a lot about clustering. This idea of finding out what are the clusters, what are the assignments of data points to groups. And just for the purposes of having something concrete to talk about, let's suppose we're talking about topic modeling. So maybe each of these data points is some article, article in a newspaper, and some of them are about sports, and some are about econ, and some are about art. So another way that we can represent this clustering is in a matrix-like form. I want to emphasize it's not actually a matrix because there's no ordering on the columns. But it's a nice way to draw it. And we can see that very easily that articles 1, 2, and 7 belong to a cluster together. Articles 3 and 5 belong to a cluster. Article 4 belongs to a cluster. And if we make this assumption that we talked about early on of exchangeability, that the ordering of the data points doesn't matter, we're effectively saying, hey, we could have seen these articles in a different order, and the distribution of them should not have changed. And now we've seen a couple of ways to generate such an exchangeable distribution. So let's just go over those. So in all these cases, we had some mass from 0 to 1, and then we divided it up. So one way we divided it up was in the case where there were a finite number of intervals in this partition. We could have gotten that from a Dirichlet distribution. We could even take Philippe's idea and put a prior over the number of elements in the Dirichlet, but it'll still be true that every one of these partitions in every case is finite. But we also saw a way where, in fact, we would have an infinite, a countably infinite number of partition elements, and that was the GEM, which we saw was part of the Dirichlet process. Now, in both of these cases, the way that we actually drew the assignments of data points to clusters was the following. We said, hey, let's put down, to draw our assignment of data points to clusters, let's put down a uniform random variable independently of the way that we drew that partition. And we'll say that when two of these random variables, two of these independent uniform random variables fall into the same group, those two data points belong to the same cluster. So 1 and 2 belong to the same cluster. 3 starts a new cluster. 4 starts a new cluster. 5 belongs with 3, and so on. OK, so actually, it's pretty easy to see that this is going to be exchangeable. If I permute any two of these IID uniform random variables, I'm clearly not changing the distribution of the clustering. And in fact, we can see that that should not depend on this being generated from a Dirichlet or a GEM. Literally any way that I could generate this partition, that would be true, as long as it was independent from the IID uniforms. Now, the really amazing thing is that Kingman in 1978 showed the converse is true. That if I have any exchangeable clustering, all I know is that it's a clustering and that the order doesn't matter, then this random partition must exist. There must be a random partition. It could be random. It could have a countable infinity of elements. It could have a finite number. It doesn't matter. But if I find such a random partition, or there is such a random partition, and I can put down these uniform random variables and recover the original distribution of my assignments of data points to clusters. OK, so why is it called a Kingman paintbox? Well, you can think of each of the clusters as having some color associated with it. Perhaps more concretely, you could think of those as being like the cluster-specific parameters like econ or art or so on. And I want to come back to this point that we made really early on about definity as being a motivation for Bayesian inference and a motivation for nonparametric Bayesian inference. In particular here, we see that it motivates a prior, well, first of all, it motivates these parameters that we didn't assume, row 1, row 2, row 3, row 4. And it motivates a prior over those parameters, that there's some random distribution of them. And we have to allow infinity for this to be true. And so that's a motivation for this non-parametric Bayes approach. OK, so a few points. Not only is this a fun fact that we can all enjoy, but it actually has some meaningful implications. And so let's think about those implications. So first of all, one is, hey, we can say something about the cluster sizes in this model. That, if you think about how many data points are going to belong to the cluster with size row 1, well, by the law of large numbers, it's going to be row 1 times n in the limit. So let's say you have an application where your cluster sizes cannot grow linearly with the number of data points. Like maybe you're in a census application and your clusters are people with different census records. Well, probably one person does not have 1 million census records. Certainly does not have some proportional number of census records to the total number of census records. And so that would be a case, coming back to Philippe's comment from earlier, what if we want sort of evenly sized clusters? You can't get that here. Not without a fixed number of clusters. Yeah?
Clarify what you mean by a cluster is exchangeable? Like, what is the measure that is exchangeable?
Yeah, so in particular, what we're going to say is that actually the thing that we're working with is a partition of the integers. So this is the sort of technical way to be very careful about that matrix-like object that I talked about before. So to say that data points 1, 2, and 4 belong together. Data point 3 belongs on its own. 5 and 6 belong together. And so what I mean is that the probability of this is unchanged by any permutation of the integers from 1 to 6.
And this probability is defined for subsets of all subsets.
Yeah, exactly. So here I'm just writing a matrix because it's sort of visually appealing, but again, there's no ordering here, and so it's really effectively a way to represent a partition. Yeah. Okay, so this is one implication. Also, a related implication is that there are stationary proportions. That the probability of this cluster or this component is rho 1, and it's always going to be rho 1, and that's never going to change. And so what if you need something that's time varying? Like, let's think about, the reality of the New York Times is that, yeah, maybe it's exchangeable around right now. But there's probably a very distinct difference in the number of articles over time that were about, say, the Nixon administration. There was probably a long time where there were not articles about the Nixon administration. Suddenly, there were a lot of articles about the Nixon administration. And then I would say today there are fewer articles about the Nixon administration. And so we want to say sometimes that actually these proportions can change, that actually things can be time varying. And so I'm going to start pointing out some talks for the rest of the workshop. The first I'm going to point out is Trevor Campbell's on Tuesday at 1:45, which will talk about a more local form of exchangeability, one that depends on covariates like time or space. Because maybe we think things are roughly exchangeable nearby in time, nearby in space, but we don't think that they should be so exchangeable farther away. Okay, so this is clustering, and we're starting to get a sense of, hey, the Dirichlet process is an example of this broader set of exchangeable clustering models, and so it inherits from that some of the limitations of that broader set of models. Can we apply the same kind of idea in other areas? Well, let's talk about networks and graphs. Okay, so we've talked about the Kingman paintbox for clustering. Let's talk about networks and graphs. Okay, so networks and graphs, there's tons of network and graph data. Again, I'm thinking about things like social networks, biological networks, transportation networks. And we might want probabilistic models for these for the same reason that we want them in any other case, that we can incorporate expert information. They could be relatively interpretable relative to some modern machine learning methods. We can flexibly build up these generative models we've been talking about. And we can get coherent uncertainties from the probabilistic framework. Okay, so there are a ton of probabilistic models for graphs. You may have heard of the stochastic block model, the mixed membership stochastic block model. Actually, there's really a ton of these. I could spend the whole hour and a half just going over models of this. So how about you just take my word for it that there are a million of these models. And in particular, if you want to read more about them, there's this nice Lloyd et al. 2012 paper that overviews them. And of course, there have been many more since then. Now, let's talk about all of these models at the same time, just like we did about all clustering, exchangeable clustering models a moment ago. So in particular, let's first make a very, I think, simple assumption. If we assume that adding more data doesn't change the distribution of earlier data, like let's say you get a new email in, you're looking at an email network, like people emailing between each other, it shouldn't be that you get a new email and that affects the old emails in any way. Like they're still there or they weren't. If you assume that, then it turns out that every one of these models, including the many more, only generates dense graphs in a way that I'm going to make precise in the next slide. You could think of dense graphs for the moment as being graphs with too many edges. And so that could be a form of model misspecification if you don't want dense graphs. And so I'm going to point to a number of talks that are going to be in this workshop and some other work, probably very briefly, about how we can learn about this from exchangeability and then come up with new frameworks for sparse graphs. Okay, so first let's discover what exactly is the problem. What is a dense graph? So here we're going to talk about graphs. So we have a collection of nodes and vertices. And in particular, we're going to talk not just about graphs, but about sequences of graphs. So we start off with some collection of nodes and vertices, and at each step in this sequence, we will add nodes and we will add vertices, or both or neither, but we'll never subtract anything. So here we happen to add a node. Here we add some nodes and a vertex, or sorry, and an edge. I meant edge. Here we add some nodes and edges. And so we have these collections of nodes and edges. Okay, and so we'll say that our definition of density for the purposes of this talk is that if the number of nodes goes to infinity, so that's like having our number of data points go to infinity earlier, we'll say we have a dense graph sequence if the number of edges grows quadratically in the number of nodes. So you can see why this might be bad, because if you think about if you had all possible edges between nodes, that would be like number of nodes choose 2. And maybe we don't always want a complete graph. Maybe if you think about how you interact with people on Facebook, it's not with all of the people on Facebook. It's not even with a proportion of the people on Facebook. Okay, and we'll basically take the weakest possible definition of a sparse graph sequence for the moment. We'll just say the number of edges is subquadratic in the number of nodes. Okay, so if we do that, let's think about what's a natural notion of exchangeability for graphs. Well, we can think of a particular sequence, and this is the type of sequence that every one of those models I told you about before does. We can add just one node at every step. And so in that case, we can label the nodes by the step on which we add them. So the first node gets added on the first step, the second node gets added on the second step, and so on. And the way we'll add edges is we'll add an edge to every node that has a lower number. And if we add it on a particular step, it'll always be there. And if we don't add it, it'll never be there. So here we'll never again see an edge between 3 and 2 or 3 and 1. Here we'll always see an edge between 4 and 1 going forward. Now we just keep doing this, and what's a natural notion of exchangeability? Well, maybe we think that if we put probability distributions over these graphs, that maybe they shouldn't change if we permute the nodes. That's like permuting the data from before. Like, hey, I'm analyzing Facebook's graph. I don't know who any of these people are. They're all kind of the same to me. So maybe I think the probability shouldn't change in this case. OK, well, let me tell you a way that we could generate an exchangeable graph of this sort, or sort of to emphasize what we're exchanging, a node exchangeable graph. Here's a way to generate such a node exchangeable graph. First, let's choose a function. It's a function that takes two inputs, x in 0, 1 and y in 0, 1. This function here is in gray. It goes between 0, 1 itself, so its values can be interpreted as probabilities. Now, it could be random, and this could be just a realization of it. And to generate our graph, for each node, we're going to put down a uniform value between 0 and 1. And I'll draw it here, and then I'll just draw it over here, too. So I only actually generated one value, but I put it here twice. Now, I'll do this again for the next data point, the next node. And wherever these intersect, that's a possible edge. And the probability of that edge is exactly the value of w at that intersection. OK, so I draw a Bernoulli draw with probability equal to w at that intersection. And maybe in this case it's a success, so I keep an edge. I look at the two possible intersections when I add the new node. This has some probability, and this has some probability based on the values of w. I draw those Bernoulli coin flips. Maybe in this case they both happen to not exist, and so we don't have edges. OK, now no matter how I draw w, the thing that you can see pretty straightforwardly here is that these are uniform random variables, just like before, IID uniform random variables. And so if I permute any two of them, I don't change the distribution of this graph. So this is going to be an exchangeable graph. And in fact, this relates to sort of nonparametrics, just as our clustering did before. So before we said, oh, we had this, partition of the unit interval, and we could do it with a Dirichlet, we could do it with a GEM. Same thing here. We could have some parametric model for W, we could have some nonparametric model for W. And a number of these are discussed in this Lloyd paper. But what's amazing is that Aldous and Hoover showed that the converse is true. That if I have any node exchangeable graph, then there must be such a W such that I can make these types of draws and recover its distribution. And this is the idea of a graphon. So every node exchangeable graph has this representation, just like every clustering, exchangeable clustering, has the Kingman paintbox. OK, in fact, we can show, using this representation, that the number of edges grows quadratically in the number of nodes. I think we're a little short on time, so I'm just going to leave that to you. It turns out it's pretty straightforward. In fact, you can show that the number of edges, not only in expectation, but almost surely, grows as c times the number of nodes squared. C can either be 0 or non-zero, and so our graph is always going to be dense or empty. And so now here's the exciting part. We just go back to that long list of graph models from before, and we notice that they're all node exchangeable. And so it follows as a corollary of that, that their graph sequences are always dense or empty. But empty is pretty boring. So they're always basically dense. And this seems pretty reasonable. You look at a given node, and all of their nodes kind of look the same to you. That's part of this assumption. I'll point out, so we've seen these symmetries now at this point, basically these exchangeability symmetries and how they affect us for the purposes of clusters and graphs. There's this great paper by Orbans and Roy in 2015 that sort of, I would say, emphasized this existing problem from the Aldous-Hoover theorem and from this graphon representation to the Bayesian nonparametrics community. And Peter Orbans will be talking about different types of symmetries and their implications on Monday at 11:30 a.m. We're also going to get a lot of great talks about how do we deal with this problem. So in particular, the obvious next question is there something we can do? And I think what's really exciting about having shown this for all these models is we know we can't work in the same framework of models. something you might have thought is, hey, I'm just going to make another model, and maybe that model will get away from this. And we know that if we work within the node exchangeable framework, we will not get away from this. We need a whole new framework to deal with this. And so there are many ideas. This is just a very short list, but luckily we're going to be seeing some very cool talks on this in the coming week. So one of these ideas is GraphXs. So Jennifer Chase and Christian Borgs will be doing a talk on GraphXs. They'll both be doing talks on GraphXs on Monday. Another issue is not just this global notion of sparsity, but actually things are locally dense often. You talk to your friends, and your friends are often friends with each other. And so Sinead Williamson will go even a little bit farther and talk about both of these problems at the same time on Wednesday. And then finally, I'm just going to wrap up with a very quick discussion of an alternative framework that we've worked on, and also Crane and Dempsey have worked on, so definitely check out their work as well. They've done some excellent stuff. Where I think we just take a pretty obvious idea, which is, how about instead of exchanging the nodes, we exchange the edges? So let me just say very briefly what this is. So before we said on each step of the sequence, we'll introduce a node. Now we say on each step of the sequence, we'll introduce an edge. So we can order the edges by the steps on which they occur. So we have the first step, the second step, the third step. You could think of this as emails coming in. Maybe we're interested in a relational network, and each of the node is an individual, and they're sending some emails. And so here we have an email between two individuals. And just as previously we brought in the edges as we brought in the corresponding nodes, now we're going to bring in the corresponding nodes as we bring in the edges. So here we bring in two nodes that sent this email. Here it turns out there's another person that's been added to the email correspondence. Here this is between two people we've seen already. And here are two new people sending an email. And now we might say, hey, what's the notion of exchangeability that we could have over this? Well, maybe we think that I'm analyzing all of these emails, and the order of the emails doesn't really matter. Again, I want to emphasize that is an assumption, and it's not always the right assumption. But it's an alternative assumption, and one we could make. We could say, hey, I don't think the order of the emails matters. And then that would be my notion of exchangeability. And what's cool about this notion is that we can get sparsity with it. If you work in the edge exchangeable framework rather than the vertex exchangeable framework, the node exchangeable framework, you can get a very wide range of sparse graphs, very wide range of sparse behaviors, lots of different sparse growth sequences that are purely subquadratic. And what's also cool is we can get one of these exchangeable characterization theorems, one that's very similar to the Kingman paintbox, it turns out. And so we can see what are the downsides of this method, because I think hopefully something that we've learned today is that every method sometimes works and it sometimes does not. And it's really about what are the assumptions that goes into that. When should we apply that method? When should we apply that model? And understanding those assumptions. Okay, so let's just wrap up here. Let's recall what we've done here. We started by talking about clustering. We introduced the Dirichlet process, which is sort of this very classic non-parametric Bayesian process for clustering. We talked more generally about what does exchangeable clustering look like. It looks like the Kingman paintbox. And so there's some sense in which we can see now that things like the Dirichlet process, the Dirichlet distribution are very natural. They're examples of a Kingman paintbox. It also tells us what models we could consider that are exchangeable and how to get beyond exchangeability. We talked about how non-parametric Bayes lets us learn more as we get more data, that there's this notion of an infinity of parameters that lets us have a growing number of realized parameters, and how we can actually do that in practice, how that's not totally impractical. And then finally, we talked about how, in fact, we can look at these characterization theorems, these Di-Finetti-style theorems for other types of data. Here we talked about networks and graphs, and that is obviously not the end of that story. There's been a lot of work recently on Di-Finetti characterizations theorems for other types of data beyond networks and graphs, beyond clustering. And so finally, how does this help us think about non-parametric Bayes and Bayesian inference? Well, it helps us understand some of the limitations of these methods. What are the assumptions that are going into our non-parametric Bayes, our Bayesian methods? We could say something about all exchangeable cluster models at the same time. We could say something about all exchangeable network and graph models at the same time. And so we don't have to just sort of keep coming up with models and think about, are they going to be useful? We know that if they're in a certain framework, they might not be for a certain point. And so that'll help us develop better models going forward. And I'll just finally end by saying again, I'm going to put these slides up on my website. I'll also be putting them up on the workshop website, and I believe there'll be eventually video for this. And if you're interested in learning more about non-parametric Bayes, Bayesian inference, things like that, you might also check out this tutorial's website as well. Thank you.
Time for quick questions, yes.
No, not at all. I guess I would say more, I don't know that I would frame any of this as a quest for exchangeability. I think it's more like, here's a way that lets us talk about all these existing models at the same time instead of going through every one of them and worrying about, like, does this model work for something? Does this model work for something? It's a nice framework that lets us talk about a lot of models. And so that was what was nice about node exchangeability. And then the hope would be for any framework you have going forward, or any model you have going forward, really, what framework does it fit in and what are the properties of that framework? And so I think it's more of a way to just talk about properties, and it's sort of a efficient way to talk about properties.
So maybe a very basic question. As a computational biologist, for me the identity of gene is more important because the network structure for gene correlation networks, or even in single cell classification problem, the property of gene is more important and identity is tied up to that.
Mhm.
Now when you say this exchangeable business, but keeping the network structure intact but changing the
Well, so I guess I want to say, like, just as, so we spent this time talking about, like, here's a specific model for mixture modeling, and then we said, here's a framework that it fits in. It's this exchangeable clustering framework, and that framework doesn't tell us how to do mixture modeling. It doesn't tell us, how to learn those clusters. It doesn't tell us anything like that. It just lets us critique the other models that fall into that framework. And so I would say the same thing for network models. Looking at the Aldous-Hoover theorem, looking at Graphons, looking at edge exchangeability, looking at Graphx's, things like that, it doesn't tell you what to do. You still have to do the work of saying, how am I actually going to learn anything from this? It just tells you that, let's say you came up with a way of learning from this and it fit into this framework, then you could critique it from within the framework.
I hope it's not a coffee stopping. So if I took the, let's say, the Graphon model, which is the dense, and then sort of do sparse sampling, and then that is a sparse model.
Yeah.
Now, how does that relate to, let's say, the edge exchangeable?
Yeah, so what changes about it is that you don't have the infinite exchangeability anymore. Like, basically, you change your model somehow as you get more data because you have to change the level of sparsity that's happening. And so it's in some sense, it's similar to, like, well, that could be fine for what you're doing. It sort of matters, do you care about how it changes as you get more data? And so this is, the way that it relates to exactly what I said is that projectivity assumption. So that eliminates sort of the sparsification ideas that one could use to get around this.
I don't see a problem with that, but maybe I'm missing something. Would it also be possible, for instance, to have several infinite dimensions? For instance, think about clustering. You can have, okay, you don't specify the number of clusters, you can have infinitely many. Can you also have, for instance, one component has several cluster memberships, for instance, so maybe infinitely many?
Absolutely. Okay, so there's an idea that gets beyond clustering where you say each data point could belong to multiple groups. So this comes up, for instance, actually in topic modeling all the time. Because really, if I read an article, maybe it's about some new movie, maybe it's about Moneyball, which was about economics because it was about investing in players, it was about sports because it was about baseball, and it was probably going to have arts words if it was a review because it was a movie. And so absolutely this comes up and is given a couple of different names. So one is topic modeling, but another one is feature allocations. And so actually there's a study of feature allocations as a generalization of partitions. And in fact, a study even of that. So you can think of a generalization of partitions where each data point can belong to multiple groups. But you'd also think of a further generalization where each data point can belong a different amount to multiple groups. And there's actually a pretty straightforward generalization of the Kingman paintbox to these cases. And if you're interested, I encourage you to check it out in our paper on, let's see, which one is it? Exchangeable trade allocations. And actually, we have an earlier paper on this feature allocation idea called Feature Allocations, Probability Functions, and Paintboxes. But yeah, I think this idea is great. There are so many things beyond clusters, beyond networks that we haven't talked about. Trees are another one that comes up. So many things. And we can think about what are the relevant notions of exchangeability and what are their properties in those cases. Yeah.
Okay, well, maybe it's time for take a coffee break and we'll reconvene here at 3. And let's think
Great.
about it.